All right, let's take a look at approximate numbers and significant digits. Our objectives are to understand the difference between approximate and exact, and to be able to follow the rules to determine the significant digits of a number. So, a little bit of verbiage here. Accuracy and precision are definitely important depending on the context in which the numbers are used. So, what's the difference between exact, like let's say an exact measurement, and approximate? Well, with exact, there's no uncertainty. In other words, there's no potential error. There is no error at all on your, let's say, measurement. Approximate, oops, if I can spell, may be close, but it's not an exact measurement. It's just an approximation, right? Let's look at an example. If a surveyor measures the distance between two locations as 167.3, the 167.3 is approximate. A more precise measure may determine that it's exactly 167.2 feet. May determine that it is 167.28 feet. And that may be still approximate. In other words, we're getting a little closer to the actual length. Now we're to the hundredths, but regardless, there's no way to, we don't have a perfect tool to determine the length exactly, to have an exact length. So significant digits or figures will tell us, and this is what we're going to talk about today. Tells us how precise a measurement is. Okay. So, for example, when we're writing approximate numbers, we must often include some zeros so the decimal point will be properly located, like 0.003, 3 thousandths, right? Or 5,600. We got to have those two zeros in there as well so that we know it's to the thousands. Excuse me, 5,600. However, except for these zeros, all other digits are considered to be significant. When we make certain computations with approximate numbers, we must know the number of significant digits. So here's a few examples, and then we'll go to the rules. So 34.7 has 3 significant digits. 3. 8,900 has 2. Because we're assuming that the 2 zeros after are just placeholders. 706.1 has 4 significant digits. The 0 is between those 2 significant digits, and then 5.90 actually has 3 significant digits. That 0 is not necessary as a placeholder. It should not be written unless it is significant, so the 0 is there for a reason. In other words, it's accurate to that position, hundredths position. Okay. So what are the rules then? Those are some examples. Let's determine the rules. Number 1, all non-zero, anything besides 0 is a significant digit. Any zeros between significant digits will also be included as significant. For example, this right here, see how the 706.1, the 7, 6, and 1 are non-zero, so those are definitely 3 significant, but the zeros between them, so that this actually has 4 significant digits there. Okay, that's that rule number 2. Zeros placed at the beginning of a decimal problem or before other digits are not significant. So call this leading zeros are not significant. That's rule 3. Leading zeros are not significant. Okay. And finally, rule number 4, zeros used as placeholders are not significant. Okay, so like that one would be like right here, 8,900. The 0 and the 0 there just as placeholders, so it's just the 2, 8, and the 9. So there's only 2 significant digits in that. Okay. So let's do some examples. We talked about that fourth rule, zeros used as placeholders. So 87,000. So there's just 2 significant digits there. The 000 just used as placeholders. 408,000. The 4 and the 8 non-zeros are definitely significant, and the 0 between them are significant, but these are just placeholders again. Placeholders. Those are placeholders. All right, so 3 on 408,000, there's just 3. The third example there, the 4.005. So notice the 4 and the 5 are significant, and so the zeros between them must be significant as well. So you include all 5 numbers. All right, again, the rule number 2 was zeros placed between 2 significant digits are also significant. 0.004. So you have those, see the 0.00? Those are just there as placeholders, or leading zeros, if you will. So those are not significant, so it's just the 4. Your leading zeros or placeholder zeros there. Okay. Now notice on this one, the 4.000, the 0.000, those are not required, right? They're being included for a reason. So they're not required, so they're counted as significant digits. Again, notice the commentary on that. So again, 4 significant digits. All right, 0.000. Again, these are placeholders or leading zeros, right? Leading zeros, so those are not significant. So it's just the 5. Whoops, it's just the 503. 5 and 3, of course, and then the 0 between them, because the 0 is between significant digits. So 3 significant digits on that. All right. You know what? Let's do a few more here. How about so those are leading zeros, so you just have 2 significant digits. Let's do another one. Let me go back to this for a minute. 87,000 we know has 2 significant digits. These are just placeholders. 2 significant, right? But if I had 87,000 and I put a decimal there, now this has 5 significant digits because of this decimal. Now you got to include them all. They're not just placeholders because of that decimal right there. Okay, so there is a big difference between the two. And let me do one more here. How about 10.0? How many significant digits does that have? And it has 3 significant digits. Okay. Now I'll do one more here. How about Here. How about 0.00700? How many significant digits does that have? These are just leading zeros. So you're going to include the 7 and the 0 and the 0. The last two zeros are unnecessary, so you got to include them. They're included for a reason, so there's 3 significant digits. 3 significant digits circled there. All right, let's keep going. The accuracy of a number refers to the number of significant digits. So the accuracy, number of significant digits. Precision of a number. Precision of a number is the decimal position of the last significant digit. Okay, decimal. So accuracy, number of significant digits, precision, decimal position of the last significant digits. Oh, whoops, I showed the answers on that. But I say, well, first of all, how many significant digits does 321.04 have? And I say there are 5 significant digits. So the accuracy, as we say, the accuracy, the number has an accuracy of 5 significant digits. Right? 5 significant digits, that's how accurate it is. And the precision, so the last significant digit is in what position right there? We say, well, that's the 100th position. So the number is precise to the 100th position. Again, the last significant digit there. Okay. All right, let's say you're measuring, I should have put the answer on here, an electric current with 2 ammeters. One ammeter reads 0.031 amperes and the other reads 0.0312. First of all, how accurate is it? So let's talk about accuracy. So 0.031 has 2 significant digits. 0.0312 has 3. Both of them have a leading 0 there. 3 significant digits. So this one is more accurate because it has more significant digits, right? Now let's talk about precision. The first one, the last significant digit, is to the 1000th position. The second one is to the 10,000th position. So the second reading is more precise. Not only is it more accurate, it's also more precise. A machine part is measured to be 2.5 centimeters long. So let's talk about accuracy first. So we have 2 significant digits. And then it's coded 0.025 has how many significant digits? So 0.025 has 2 significant digits. That's just a leading 0 placeholder there. So we conclude, as far as accuracy is concerned, same accuracy. Okay, let's go to precision. So with precision, here's our first one. It was measured 2.5, so that's the tenths position. Second one, 0.025, with the thickness of the, what was it, coat of the film of that thickness. So that would be the tenths, hundredths, thousandths position. So I would call this one. So this one's more precise. So the thickness of the film is measured to a greater precision. Then they measured the length. All right, why don't you guys try this one? So the 9270 has 3 significant digits. The 0 there is just a placeholder. And the 0.8 only has 1, so the 9270 is more precise. Whereas the precision, the last significant digits to the tens, whereas on the 0.8, that's in the, oh, I'm sorry, that's not the thousandths, that's the tenths. My apologies. But either way, tenths is more precise than to the tens position, right? So, all right, that's it. I think that'll kind of get you started on the. Oh, I'm sorry. I do have a few. I forgot to talk about greatest possible error. Let me keep going here. My apologies. All right. Just a commentary here. When we measure something, say a distance 176.3, we're saying that the length is at least 176.25 and no longer than 176.35. Any value between these two round off tenths would be expressed as 176.3 feet, right? Another way to say that is if you're measured to the tenths position, then let me write this down. So here's 176.3. So if we measure the last of the tenths position, what's called the greatest possible error is you take that position, so tenths position 0.1, and you take half of it. You take half of that. So 1/2 times 0.1, you go ahead and you punch that in, you get 0.05. So you could be 176.3 plus 0.05, or as low as, write this, as low as, or as far, you could be as far off as 176.3 minus 0.05. Well, 176.3 minus 0.05 gives us 176.25, and that gives us 176.35. So that's called our greatest possible error. There's another way to say that. We'd be as low as that or as high as that. Okay. Now, rounding off. Well, and this is not your classic rounding off thing that you're thinking of. This is rounding off based on number of significant digits. Okay. So what you do is, number one, you determine the number of significant digits. Number two, consider the digit in the next place to the right. If it's less than 5, we accept the digit in the last place. If it's greater than 5, we increase it by 1, right? So for this one, 70,360, we look at the last significant digit there. And we say, well, it's 5 or greater, so we're going to bump that up to a 4. So that's where we get the 70,400, right? On the 70,430, now I'm looking at the 3 right there. And I'm going to round that to since it's a 3, I'm going to leave the 4 the same. So 70,400, right? And make that a 0. 187.35. So right now, again, it has 5 significant digits. We're going to go, so the last position, let me go ahead and write that, 187.35. There's our last one, so we're going to bump that up, 187.4. Right, we're going to round it to 4 significant digits. And finally, 71,500. My last significant digit is 5, right? So I'm going to bump that up. 72,000. That's your procedure for rounding off based on the number of significant digits. All right. When we're going to do number 1 first here. When approximate numbers are added or subtracted. Okay, so added or subtracted. When it's addition, subtraction, the result is expressed with the precision of the least precise number. The least precise number. Okay, whereas on the other hand, when you're multiplying or dividing, it's the accuracy of the least accurate. So we use the smallest number of significant digits. Okay, and then for roots there, we're not going to get into roots. So let's do some examples here. So let's say here's our number, 73.2, whoops. 73.2, 8.0627, 66.296, right? So let's say we add them all up. Right, here's our addition. Add them all up. And remember, adding and subtracting is the precision of the least precise number. So our least, I look at the last significant digit. So that's the precision to tenths. That's a precision to 10,000ths, hundredths, thousandths. This one's the least precise. So when I take this, I got to round it to the 10th position. So I look at the 2 to the right. And since it's just a 2, I leave the 241.1. Adding and subtracting is the least precise. So you take the least precise number, and you're only as good as your worst precision. Your measurement's only as good as your least precise number, right? The least precise is to the tenths here, so you want to round it to the tenths. Okay? All right, let's do another one. So let's say we are dividing. So we're taking 292 divided by 3.4. So 292.6 divided by 3.4. And if you remember with multiplication, you go to the accuracy of the least accurate. Well, accuracy is the number of significant digits. This has 4 significant. This only has 2 significant digits. So we get this number right here. We do the division, but we can only go to 2 significant digits. So the ones position. So I look to the right. It's a 0, so it just leaves it as 86. We're just going to round it to 2 significant digits here. Okay? All right. Last thing, I do want to talk a little bit more about greatest possible error. So what you're going to do is you're going to find the half of the measuring unit of the last significant digit. So you go one. Let me do find the greatest possible error, and that's called GPE. The initials GPE, greatest possible error. Find the greatest possible error of 14.6. Well, this goes to the 10th position. So it's half of 10th position, 10th, so 1/10, 0.1. So go half of 0.1 is 0.05. That's your greatest possible error. So it could be as small as 14.55. As low as, I could be off, or it could be as high as 14.65. That's what we're saying. Let's do another one. Let's say we have greatest possible error of 14.67. This one now goes to the hundredths position. So I'm going to take half of 1/100th. I get 0.005. That's my greatest possible error on this. So this could be 14.665 or 14.675. It could be as high as that. And last one for greatest possible error. Let's say I have 35.678. Now I'm to the thousandths position. Is my greatest possible error. Okay, hope that helps you guys. See you next time.